Hi guys, welcome back.
Hello.
If you look at my background here, I want to demonstrate the power of electrons. This is an actual thing that was created by my physical therapy students at Carrington College here, teaching in my physics class. But if you look at it, all you see is a battery. That yellow disc is I haven't seen your moment here, magnet and copper wire, both covered and uncovered. The electrons are obviously being generated by the battery, which are traveling through the copper wire. Now, electrons, like you saw in J.J. Thomson's work, that they have with it, any charged particle has a magnetic component with it. And so as the electrons are being traveled, the magnetic component is being attracted by the yellow disk, which is the magnet, and then momentum just keeps it growing over and over again. So electrons traveling through, this is a perfect example of electrons used to create a motor. Now we can reverse it and take the power out of there and play with the rotation of that coil and the magnet and reverse it and actually create electricity. Hence we have things like a generator and so forth. But those are the same type of subatomic particles that you find all around us, from static pain to the electrons that are going through your body, doing all kinds of interesting things. Anyway, let me remove that because that gets a little distracting. Where'd it go? Okay, hope everybody's doing okay. Now, a quick reminder, we have on Tuesday the next online exam. Again, to remind you, it will open up at 7 a.m. on Tuesday and then shuts down at 11:59 p.m. that same day. So don't forget about it. Give yourself plenty of time. Same amount of time limit, 75 minutes. Previous experience shows that it takes approximately about an hour to complete. So give yourself plenty of time. Please don't wait until 11:58 because they will kick you off. Canvas will kick you off. All right, so we were talking about electron. Well, before I begin, does anyone have any questions? Maybe previous stuff we talked about, or chapters 4, 5 through 6, which the exam's all about. Don't forget, I'm here on Mondays from 1 to 2, most of the time by myself. So if you have any questions, feel free to drop by and I can help you out with some questions. Okay. Well, if not, let me continue then. We had stopped in the next slide, but to refresh your memory, what we're doing is here determining the Lewis dot structures of compounds. Now, the Lewis dot structures of atoms are pretty straightforward in that you draw the formula, write the formula for the atom, determine how many valence electrons it has, and then simply put down how many dots that represent the electrons around the atom, okay? And those are for groups 1 through 8A. You can't do that type of prediction for the B elements, only for the A. So we take that one step further and we start looking at structures and, in which we come up with this particular type of structures. I suggested to try these on your own, see if you can come up with the same structures that you see here, okay? Now, why do we want to do this? Well, we're going to eventually talk about the polarity of these compounds, which is related to the polarity of the bonds that they create, which is related to the electronegativity of the atoms that are involved in that particular bond. Once we determine the polarity, we are able to predict a variety of different properties for that compound. We can predict such things as boiling point. We can predict such things as, is it soluble in a what we call a polar solvent versus a non-polar solvent. And a classic example of a polar solvent is water. Water is the most polar liquid out there. There's one a little bit more, but water is by far the most polar liquid that we have. And then the other end of the spectrum is what we call non-polar. So an example of a non-polar solvent would be oil. Oil is made up of non-polar chemical bonds. And then keeping the general rule of thumb that like dissolves like, we can actually do some predictions. So a polar compound would be more soluble in a polar solvent and less soluble in the non-polar solvent. Okay? Now, to give an idea, to refresh your memory so you can understand polar versus non-polar solvent, the perfect example is Italian dressing. If you're familiar with that, you look at that bottle, you got two layers. You have an oil layer and an aqueous or water layer, okay? They do not mix. We all know that oil and water do not mix, so they separate. And they don't mix because of the polarity, which they don't mix because further down because of the chemical bonds in which are involved. So we did a specific example, and we took the HCN example, and what you do is first step is you add up all of the valence electrons that are involved in that structure. Notice here that you will always be told what the center atom is. In chemical compounds, or at least for the majority of the ones that we'll be working with, there's one atom that is a central atom. Everything else around it, be it hydrogen, oxygen, nitrogen, or whatever other atoms there, would be bonded to the central atom, okay? So we add up all the valence electrons from every atom, so we go find it on the periodic table, what group they're in, that tells us how many valence electrons. And so in this example, we have hydrogen, which brings 1 valence electron, carbon, which brings 4 valence electrons, being in group 4, and nitrogen bringing in 5. So we have a total now of 10 valence electrons. That is what you got to work with. We can't add more valence electrons, and we can't subtract them. So 10 is what you got to work with. I like to divide, you're going to find that number divisible by 2. So I like to divide it by 2 and figure out how many pair. Okay, how many pair do I have to work with? Because I can simply just draw a line. A line represents a bond and represents 2 electrons. Okay, so I can, here at this example, quickly draw hydrogen, because I know that carbon is the central atom. I quickly attach the hydrogen and the nitrogen to the central atom. And that takes care right there of 2 pairs. So that means I got 3 left to work with. Now, where you put them doesn't make a difference, except you can't put them back on hydrogen. Why? Because hydrogen's duet has been fulfilled. If you look at that structure there, we got a line or a bond between the carbon and hydrogen. Those 2 electrons are being shared by hydrogen and carbon. And so they can be counted toward hydrogen as 2 or toward carbon as 2, okay, because they're being shared. The nitrogen is sharing that 1 bond, okay, so we got to put them either on the carbon or the nitrogen. And whichever one you put them on, it makes no difference. So we do that, and I can put them in this example here. And so if we look at that structure that I just drew, you notice that every line again represents a pair of electrons. We still have 5 pair. So once you put them together, you got to stop and count them. Make sure that you still have 5 pairs. Occasionally what can happen, you can inadvertently forget a pair and you end up short, or you can inadvertently add another line and add more, okay? Now at this point, we start looking at the Octet Rule. And so you want to adjust those electrons that you have to work with by creating either a double bond or a triple bond. That's as many bonds as high as you can go. There's no such thing as a quadruple bond. It's either single, double, or triple. And we take one or two more pairs of those electrons, and then we create a double bond. And we keep doing that until such time that the octet is fulfilled. And so in this example here, we have this particular structure, where now we go check the octet again to make sure everything is on the up and up. Okay. Someone had a question or it disappeared? Oh, there it is. Oh, we're on chapter, Rosella, we're on chapter 7. Okay, no problem. Okay, so if we look at here at that nitrogen, just take a look at nitrogen all by itself and count the electrons around the nitrogen, whether they're bonded or not bonded. Okay, we'll see we have 2, 4, 6, 8 electrons around nitrogen. So nitrogen's octet has been fulfilled. If you do the same thing for the carbon, isolate the carbon and count the number of electrons around carbon, again, regardless if it's bonded to whomever. So in this case, you see there are 4 lines or 8 electrons. And so its octet is fulfilled. And then finally, check hydrogen. And hydrogen has 1 line attached to it, because those are the pair of electrons that are being shared with carbon. And it has 2 electrons around it. So its rule of duet has been fulfilled. So this particular structure is what we propose to be the structure of HCN, okay? All of the valence electrons are accounted for, all the bonds are accounted for, the octet has been fulfilled. And so what do we do with this information? Well, we then create the general formula, okay, of ABE. So A is always there, because that's the central atom, there's always going to be 1. And B represents whatever's bonded to the central atom. So in this case, that carbon is bonded to nitrogen and hydrogen. So B becomes B2. That should be a subscript. I don't have the subscript function available. So and then we look for E. E represents only those non-bonding pair on the central atom. Carbon does not have a non-bonding pair. Okay, all of them are bonded. So we have 2 types of pairs of electrons. We have a bonded pair and a non-bonded pair. Okay, a bonded pair is a pair that's bonded with another atom and it's being shared. A non-lone pair is just sitting there on the central atom, not being bonded with anything. Okay, so the general formula here is AB2. With that bit of information, we go to your periodic table, actually the shapes table, and we look it up. We look for AB2. So AB2 is the first entry, where you see that the molecular geometry for HCN is what is called a linear shape. And this bond angle, and that is the bond angle between B's, is in this scenario given as 180 degrees, okay? So let's do another example. Let me pull up a...
just real quick question.
Sure.
So A will always be there because it is the central atom. I mean, central element.
Yes.
And then the B is determined by how many like different elements are attached to the central atom or central element.
That is correct.
Okay, just making sure that I
And
was just making sure that is
and E, go ahead.
is the element is this the electrons that are not bonded with the central atom, right?
You got it. In fact, we're going to do an example. We're going to do an example now of a sample of a non-bonding pair on the central atom.
Okay, thank you.
Okay, sure, no problem. Okay, let's do this one. Start from scratch. Okay, this one's called sulfur dioxide. Okay, and we'll begin with first determining the general formula, the structure for this. And this is where the Lewis dot structure comes into play. So step number one, we count up the number of valence electrons for sulfur. Uh-oh, I'm having trouble here. What's going on? Okay. Now, how many valence electrons does sulfur bring in?
6.
6, right? Right. For some reason, let me rewrite this. That is 6.
Thank you.
Something happened here causing this. Okay, that is correct. We got 6, and how do we know that? Because it's a group 6. There's 6 valence electrons. What about oxygen?
Dr. Fred?
Yes.
I'm sorry to bother you. What part
No
of
problem.
chapter 7 are we on? Is it 7.7?
You broke up.
I said, what
No,
part of
sorry.
chapter 7 are we on? Are we on 7.7 with shapes and bond angles, or?
Shapes and bonding, that should be correct. We're on slide 20 on the PowerPoint slides.
Okay, thank you. I'm sorry.
Yeah, no problem, no problem.
Thank you.
Okay. And so oxygen is also in group 6, correct? So being in group 6, it brings 6 valence electrons, but we have 2 of them. Okay, and so it brings into the whole molecule 12 valence electrons. So we have a total VE electrons, valence electrons, is equal to 18. Everybody agree on that?
Yes.
Right? Okay. And so, or I can say I have 9 pair of electrons.
Mr. Dort.
Yes.
So, so the 2 that you multiplied the 6 with, is that because like the 2 is in the title of it? Like,
You broke up.
did you multiply 6 by 2 because there's 2 of the oxygens, so therefore it would be double?
I got the is, but I'm thinking you're saying that the 2, because the subscript 2 tells you there's 2 oxygen atoms.
Yes.
Okay? Having 2 oxygen atoms, you have to multiply the number of valence electrons for oxygen times 2, because you are counting all of the valence electrons that all the atoms bring to the molecule. That answer your question? Yeah, you might. I'm not picking up on the words. Yes, Jordan, that's correct. So you double it. So if I had 4 oxygen atoms, then I would have to multiply that by 4, so having 24. Okay. Okay. So now we have a total, so we add everything up. we have a total of 18 valence electrons. And like I said before, I just divided by 2. In fact, the number that you come up with should be divisible by 2. If that's a first check to see if you got the right number. If you end up with like 17, well, something went wrong, because you won't have a number that's not divisible by 2. Okay. Right, so we have 9 pairs. So that number, 9 pair of 18 valence electrons, is what you got to work with. I can't arbitrarily just add more or take them out. I got to work with 18. And if I'm shorthanded because the octet is missing electrons from one atom, then that's where you start making double and triple bonds, like that example we did with HCN. Okay? And so now we have 18 to work with. I'm given the structure. You notice that SO2, I got S underlined, which is indication telling you that the S is the central atom. Okay? Excuse me. Or it could be in bold. Either way, you're always going to know who the central atom is. So I can very quickly draw this structure. And if I was doing it on the board, I would just draw it S line, oxygen line S line O. That's telling me that I have 2 bonds, 2 pairs have been taken care of. Now I have 9 pairs to work with. So I have, how many pairs do I have to work with now? If I just used up 2 to draw my initial forming structure, and I got 9 to work with, what do I have? I got 7 left to work with. I got to put them in there, okay? Now, where you put them makes no difference as long as wherever you put them does not violate the octet for the atoms, with the exception of hydrogen. If hydrogen is up there, hydrogen would be already content and I couldn't add any more. I would have to put them in the other atoms. All right, so I'm going to attempt to draw 7 more pair. And so bear with my drawing capability here. I'm going to just simply draw a line. All right, before I do that, let me make some space here so I can not lose that. All right, so I'm going to simply draw a line which indicates a pair. And I got 7 to work with. I like to start in the outside atoms and work my way in. There's 1 pair, 1, 2, 3, 4, 5, and 6. So right now, does everybody see there's 8 pair on that molecule? Okay, I got 9 to work with. Now, where can I put that 9th pair on? Which atom can I put it on?
The central atom?
It would have to be, because I cannot put it on the oxygens because there's already 8 around the oxygens, okay? And so the only place I can put it is on the central atom. Okay, and now do an inventory check to make sure you still got 9 pair overall, because this is where things you get lost, you forget a pair or you add a pair, and that's gonna mess up your structure, okay? But remember, you only got 9 pair to work with for 18 valence electrons. So if you count those lines, again, those lines, I repeat, are written so they represent 2 dots. Each dot represents an electron. Now, instead of having to be drawing all these dots, a straight line, a small line, represents a pair, and it's much quicker, okay? So I have 9 pair right there as we wrote it. Now, once you've done that, you check the octet for every atom. We already verified that the oxygens are full and their octet has been fulfilled. There are 8 electrons around each of the oxygen. Now, how many are around the sulfur, the central atom?
6.
6. So sulfur is shorthanded. And so I would like to say we borrow from Peter to give to Paul. So you can take a pair on one of the oxygens, either one you want to make it, doesn't make a difference, and create a double bond, okay? And creating the double bond then gives you this particular structure. Let's do this. Let me close this up. And so now I have O hyphen sulfur. I'm going to create a double bond. That's my equal and my oxygen. Now I'm going to go back and making sure that I have my original double bond, my original pairs. I had that one, that one, that one, that one, and then I had the two over here. I took the one from the right oxygen, okay? It doesn't make a difference. It could have been the left oxygen, either way, okay? Double check to make sure your inventory is still good. You're still at 9 pairs. Everybody see that there's 9 pairs still on that molecule, okay? And there are exactly 9 pairs. Once you do that, go back and check the octet on each atom. The left oxygen, we didn't do anything to that, so it's still at 8. The right oxygen still has 8. 2 of them are it's double bond, okay? 2 pairs, and then we got the 2 other pairs on the oxygen that are not bonded, okay? We call those lone pair. And then we go back and check on the sulfur. The sulfur now has 8. By borrowing a pair of electrons from one of the atoms and creating a double bond, we have now fulfilled the octet for the central atom. Unlike it was originally as we drew it, the octet was not fulfilled. If that wasn't enough, then we would make a triple bond, okay, until such point that the octet is fulfilled. So now you have the structure for sulfur dioxide, okay? Next thing we do is we write the general formula. And so it always has A, okay? B would be what? A represents a sulfur. B represents the oxygens. How many oxygens do we have? We got 2 of them, exactly. Now, notice on the central atom, we have a lone pair. It's not bonded, it's sitting on the central atom. So now, the general formula for this structure is AB2E, okay? So with that bit of information, notice how we're given the formula. We took the valence electrons, we created a structure. From there, we determined what the general structure formula is, and then we move over to the shapes table to give us a better idea of what it looks like. And we look for the general formula of AB2E. And sure enough, there it is, down in right here. Let me, we got it right here. Okay. And so sulfur dioxide has that molecular geometry. Here's the lone pair in the central atom. Those 2 dots represent the lone pair. That kind of oval shape, that's trying to show you that's an orbital sticking out there. And so it just has the lone pair on the central atom. And that shape, the name of that shape is called bent. And that bond angle between the 2 oxygens is much less than 120 degrees. Unlike up here with the AB3, where that bond angle is 120. Now, I got a couple questions here. Give me a minute. Okay. Nick, go ahead.
So the only part that I got lost on was, so I understood everything but the double bond to
Yes.
To the central atom. Why did you have to make a double bond? That's where I got lost.
Okay. Because remember, you want to maintain the octet in all the atoms.
Okay.
And if I'll go back to that slide here in a second once I'm done with this. But when we had the initial structure that we wrote, the central atom the sulfur did not have 8 electrons around it. It had 6. Okay.
Okay. So
And
doing the double bond makes it to where you share the electrons to make it 8. Okay.
You got it. Exactly.
All right. Thank you.
Okay. You get that, Jordan? Yeah, sounds like you say you got some pain. Okay. All right. So going back to this, the angle between the two oxygens for the structure we just made is much less than 120. And why is that? It's simply because those lone pair occupy a lot more space. Okay. And so what's happening compared to the trigonoplanar, the one I put a box on the top, by occupying more space, they shrink or they pull A and B further in together. And hence the bond angle between the oxygens are a little bit different, much less than 120 degrees. All right. So once we got the structure, now we call bet. Now, why is this important at this point? Okay, because now that we got the structure, I'm gonna kind of go back and introduce what we're going to be talking about here in the next few chapters. Once we figure out the structure, I lost my spot. Okay. We can now determine, where to go? Back here. The polarity of this compound. Okay, going back to where we were here. Remember we had that set up here. Lost my, okay. We have 9 pair on that sulfur dioxide. Okay, and that angle really that we see here is really not straight across. It's bent like in the shapes table. So that oxygen on the left-hand side should be more of an angle down. Now, remember we talked about electronegativity, okay? You remember that electronegativity was, can we use 2 double bonds? Good question, Brian. If we make 2 double bonds on that oxygen, what will be the problem? Let's draw it, okay? Still maintaining, wow, okay, and then Jordan, okay, you got 1, 2, you see the red lines? Maybe I'm gonna color in black, but also the hyphen, the black lines are pairs. So now do you see how many pairs there are? You counted 6 of the red lines, but you missed the one between the left oxygen, which is 7, and then the 2 between the right oxygen, which is 9. Okay? That's a good question. What I'll do is I'll change my color so we'll make sure everybody's in the right format. All right, so the question is, why couldn't I put 2 double bonds in the sulfur? Okay? So the lines in regards to color, that's correct. I just happened, my anointing tool happened to be in the red color, okay? But it's now in the black. So we're gonna answer the question why couldn't we put 2 double bonds like so? Okay, we still had 9 pairs, remember. Okay, so instead of I would have to take the lone pair from one of the left oxygens to make a double bond. So I still have those, that one, and that one. Okay, everybody, do I still have 9 pair in that structure I just drew?
Yes.
Yes.
Yes, okay. Now look at the octet for the left oxygen. Is it at 8?
Wait, can you say that one more
Yes,
time?
sir. Yeah, look at the
Yes, it is.
octet for the left oxygen. Is it still at 8?
Yes.
Okay. Now look at it for the right oxygen. Is it still at 8?
Yes.
Okay, now look at it for the central atom.
Okay, so that would be, it'd be over by 2. It would make it 10.
How many electrons in the central atom?
Would that be 10?
10. Okay, and so what does that violate?
Octet Rule.
It violates the octet rule. Okay, so putting it on this, making 2 double bonds and still maintaining 9 pair would cause you to violate the octet on some atom. In this case, it was on the central atom. Okay, and so this structure here would be totally incorrect. Okay, and so the structure that would be correct would be this one here. Now, whether you put the double bond on the right side oxygen or on the left side makes no difference for Chem 130. But if you were doing 151, 152, you actually will have 2 structures in that, because that double bond actually roams around. Okay? Okay, you got it, Jordan. All right. So that's the key. Once you put your bonds together and you think you got the structure, check the octet rule. Remember, the hydrogen has a duet rule, so that you'll never see a double bond on a hydrogen. Okay. So everything else, all the other atoms, if you end up with more than 8 pairs on an atom, then it's incorrect. If you end up with less than 8, you're incorrect. Okay? And so you want to move electrons around and still not violate the octet rule and make double bonds as needed and triple bonds as needed. Remember, we did the HCN. Okay? We needed to make a triple bond there to make sure the octet was fulfilled. All right. So now we have this structure. All right. So now it tells us, well, what do I get? What information do I get from here? Okay. Well, from now, I can look at the bonds that are created and determine what we call polarity. I kind of introduced it to you right now about polar solvents and nonpolar solvents, oil-like and water-like, because now, if it is a general rule, is when all the bonds of a molecule are polar, then the molecule would be polar in itself, which then gives you information about some forces that we're going to learn about, some forces that will help us determine such things as vapor pressure, boiling point, viscosity, surface tension. It would also tell us things like whether something is more soluble in water or more soluble in a oil-like solvent, okay? And so we started off with the atoms, remember that. Learned about those atoms, learned about the ions and what they form. And now we're beginning to put these atoms together to make compounds. And these compounds are going to give us a lot of physical properties based on their structure, which is related to the shapes table, okay, which is related to the electronegativity. Remember we discussed electronegativity? Electronegativity is a measure of the affinity for an atom to pull electrons onto itself when it's bonded in a compound, in a molecule of some sort, okay? Not to be mistaken with ionization energy, which just deals with removing an electron from an atom. We're talking about something here that's bonded to create a compound. And so you ask yourself, in that bond between two atoms, is it polar? Well, here it's very straightforward. When there are two atoms that are dissimilar, automatically you have a polar bond. Okay? I repeat that. When you have two atoms that are bonded and are dissimilar, you automatically have a polar bond, with the exception of a carbon-hydrogen bond. But more on that in a second. And so if I look at something like let me erase most of this stuff here because it's getting kind of messy. If I have something like a carbon bonded to oxygen, you're asked the question, is that a polar bond? Okay. Based on what I just said, what would be the answer for that bond between carbon and oxygen? Is that a polar bond? Pardon me?
Oh no, I thought she was asking. I said too that I was thinking about the bond right there.
Would it be yes or no? What do you think? Yeah,
Yes.
50-50 chance. Yes. Remember I said when you have two dissimilar, okay, is it a polar bond? Yes, it is a covalent bond. There's no question about that. We're not talking, because you can have covalent bonds that are not polar and polar. So the question is, yes, that is a covalent bond. No question about that. The question is that covalent bond polar or non-polar? And to answer the question, you look at it and you see two dissimilar atoms. The answer is yes. Okay. If you see a bond like this, BR-BR, yes, that's a covalent bond. Is that a polar bond though?
No.
No. In fact, you know 7 bonds right now that are not polar but are covalent. You know what those guys are?
Have no fear of ice cold beer.
You got it. Okay. Now add one more to that. So now you know 8. Any carbon-hydrogen bond is nonpolar. Yes, they're dissimilar, but the electronegativity between the two is so small, it's immiscible. And so the electronegativity between carbon and hydrogen is essentially the same. Therefore, like the diatomic elements, that is a nonpolar bond. A lot of the oils, the vegetable oils, the lard, the manteca, or the grease and stuff, they're hydrocarbons, okay? Very nonpolar bonds. The gasoline that you use, your fuel, a lot of them have carbon-hydrogen bonds, very nonpolar. In fact, we tap into this. A lot of your soaps and detergents, okay, shampoos, you have a big giant molecule. On one side, they're made up of nothing but nonpolar bonds. On the other side, have a polar end, okay? And the point and the reason behind that is the nonpolar part is the one that dissolves the greases and the oils in your body or in your clothes, and then get washed away by the polar part, which is soluble in water. Okay. And so now we know, we identify what's a polar bond, what's a nonpolar bond. Now going back to what we just did between sulfur dioxide, is the sulfur oxygen, is that a polar bond?
No.
Sulfur oxygen, think about it.
Oh,
Are
yes.
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 First question, when you're always asked that question, avocado oil, I'm not sure about avocado oil, but it's I think there's some hydrocarbons in there too. Yeah. And so if the two atoms are dissimilar, polar bond. okay, with the exception of carbon, hydrogen. Now, remember about electronegativity. Looking at the carbon-hydrogen bond down here, I just typed in, who is more electronegative, carbon or oxygen?
Would it
Now, how would
be
I determine that?
Whichever one's closest to fluorine.
You got it. Okay, remember the periodic table. Okay, fluorine is our benchmark. Fluorine is the most electronegative element on the periodic table. And so everything else, as you go toward fluorine, the electronegativity increases. So when I want to compare the electronegativity between two elements, I look to see their position relative to fluorine. So between carbon and hydrogen, who is more electronegative?
oxygen? No, wait.
Exactly. No, you're right.
Okay,
Who's
no, I
close?
was right.
Yeah, who's closer to fluorine, oxygen or carbon?
It would be oxygen.
Oxygen. And so oxygen is a lot more electronegative. So what does that mean? Let's go back to our, what that means is that oxygen in this bond tends to pull the electrons onto themselves. Now in covalent bonds, which what we have here, between two nonmetals, there's two types of bonds, which we can just describe them right now. One is equal sharing. That would be bromine and bromine, because they're both the same element. So that those electrons between the two bromines are being shared equally. And then we have unequal sharing. And that example would be carbon and oxygen, because the oxygen is a lot more electronegative than carbon. The result is it will pull the electrons of that bond toward oxygen. And hence I drew that arrow there to describe that it tends to pull the electrons. So think of it as a tug of war. If I have two bromines, I got two people of the same size, same strength, they're pulling on that rope, nothing's going to happen. That rope's just going to stay stalemate because there's equal pulling. But then I get a carbon-oxygen bond, and that would be maybe a 100-pounder versus a 400-pounder pulling on that rope. Well, obviously, it's going to go in one direction, okay? And so the electrons in that bond get pulled toward the oxygen, which results in a polar bond. Okay, this is an example of a polar bond because the electronegativity of oxygen is greater than carbon, and then we have a disparity of the electron density, which the bulk of those electrons are being pulled toward oxygen. Okay, the bottom examples where the atoms are the same or they're carbon-hydrogen, we have what's called a non-polar bond. Now, being a non-polar bond versus a polar bond defines its solubility in solvents. A polar bond would be a lot more soluble in polar solvents than they would in non-polar solvents, okay? And vice versa for non-polar bonds. A nonpolar chemical would be more soluble in a nonpolar solvent. And it's defined by the bond and the electronegativity of that bond within the molecule. So going back, go ahead.
For carbon and hydrogen, how they're not polar bonds, is that like the only one that's kind of like wonky? For non-polar bonds, is carbon and hydrogen the only one that's kind of wonky when it comes down to it not being polar bonds because they're similar?
Yeah, carbon and hydrogen is the only example of two dissimilar atoms that would be nonpolar. And then
Okay.
the other 7 are all of the diatomic molecules.
Okay.
So carbon and hydrogen is the only one, simply because the electronegativity of carbon and hydrogen are very close and very similar. They're basically the same. Okay. All right. So now, if we look at that example we did earlier, now what it was defined to, we had carbon dioxide. Okay. When you when the structure was made, carbon dioxide had the formula of oxygen double bonded to carbon, double bonded to oxygen. Okay. That's carbon dioxide, CO2. Okay. And if you go through that exercise, you will find those are the lone pairs. Okay. You will find this particular example to be short on the octet. So you have to create double bonds on both sides to fulfill the octet of carbon. You come up with that structure. And that is the general structure, which is linear. It's an AB2, 180 degrees bond angle between the 2 oxygens. Okay. Now, based on what I just stated here on the far left, I said that carbon and oxygen are dissimilar and therefore have a polar bond. Okay. And generally, when you have polar bonds in your molecule, you end up with a polar molecule. Now, having said that, can you predict if carbon dioxide is polar or nonpolar?
Polar?
Yeah. Okay, we got a 1 polar,
Polar.
and we got 2 polars, 3 polars. Okay. Negative 20 points. No. Okay, let me explain what's happening here. Okay. Yes, you're correct, because you looked at carbon and you looked at oxygen, and you said that's a polar bond. So that's good. Okay. Okay. All right. So I can draw an arrow, and I'm going to use the red color here, so I can distinguish it from all the other stuff. Okay. Now, so from carbon to oxygen, it's polar. So oxygen is pulling those electrons toward itself, which is consistent with what I just explained earlier over here on the far left with this guy. Okay. But there's 2 of them. Okay. So now on the left side, same scenario is happening. It's pulling toward the oxygen. Look at the direction of those arrows. Those arrows really mean something. We call those vectors. That's beyond the scope of this class, but basically what I can do, I can add those arrows because vectors are nothing more but magnitude and direction. So that arrow's going into the right with an X amount of force. And then the arrow to the left is going to the left, the same amount of force. Okay. The net result is that these 2 vectors, these 2 arrows cancel each other out. Okay. So though we have an example here, carbon dioxide, that has polar bonds, the fact that they go in opposite directions, they cancel each other out. So the net effect is that they are nonpolar. So carbon dioxide, even though they have polar bonds, but they cancel each other out, is a nonpolar molecule. Okay? You can test this for yourself. Next time you get a soda pop, get that bottle and shake it. What happens?
When you try to open it, it
Yeah.
sprays everywhere.
You got it. Okay,
Woo!
you make a big mess because carbon dioxide is being removed from your solution. You're losing the carbonation. If carbon dioxide was truly soluble in water, it wouldn't do that. It would stick in there. If you take the same thing with another molecule, it's not going to come out unless you kind of force it, heat it up a little bit. It doesn't really dissolve. It just forms. It's in solution, but not totally dissolved into it. Okay. And so the point is this: if you have polar molecules, you generally polar bonds. You generally have a polar molecule, unless the polar bonds cancel each other out. Okay. Unless they cancel each other out, and if they do cancel each other out, then it's nonpolar. Now, with that said, what do you predict to be the polarity of the one we just did, sulfur dioxide?
Wait, can you say that one more time, please?
I just demonstrated how carbon dioxide has polar bonds, but because the polar bonds cancel each other out, the net effect is it's a nonpolar molecule. Now let's go back to sulfur dioxide, the one we just did the Lewis dot structure. And we also figure out what kind of structure it had. What would you say as far as the polarity of SO2? Would you predict it to be polar or nonpolar based on what I just finished talking about?
Non-polar.
You know, obviously, because do whatever you do, take it out or whatever.
Okay, I got one nonpolar.
Non-polar.
Okay, two nonpolars. Okay, anybody else wanna? You got a 50-50 chance here. No, but you know, think about the structure we found that SO2 had compared to the structure of carbon dioxide. Carbon dioxide was linear. Let's go back to the shapes table. Okay. Carbon dioxide has the first structure, AB2, linear. What did we determine with respect to SO2? It was AB2E. Remember, it had a lone pair on the center? All right. So the structures, the geometry is given to you here. Sulfur's in the middle, and the two oxygens are bonded to it. Notice that it's not linear like AB2. It's not linear, like I explained, because that lone pair on the oxygen, okay, are taking up space. Now, with respect to sulfur and oxygen, who's more electronegative, sulfur or oxygen?
Sulfur?
Who's closer
Oxygen.
to fluorine?
Oxygen.
Oxygen is. Oxygen's in the same period. Sulfur is one period down. So oxygen is much closer to fluorine. Therefore, it is a lot more electronegative. Therefore, what that means is that the electronegativity goes from sulfur to oxygen. So the arrow goes in that direction. Oxygen's out there. And the arrow goes on the other side in the other direction. Unlike carbon dioxide, where we had this scenario. Okay? In carbon dioxide, those arrows cancel out. Do you think that these arrows down here for the sulfur dioxide would cancel out? No, they're going in complete opposite directions. Okay? And so remember, if a molecule has polar bonds, you can say it's going to be a polar molecule unless the polar bonds cancel each other out, as in the case of carbon dioxide. In the case of sulfur dioxide, the polar bonds do not cancel each other out. Therefore, SO2 is very polar. Okay? Does that make sense?
Yes. For some reason, I was thinking fluorine was FL, not F. So when I was looking at my periodic table, I was getting
Uh-huh.
confused.
Okay.
So I figured that out.
All right, no problem. And so sulfur dioxide is very polar. Carbon dioxide is very nonpolar. Sulfur dioxide would be much more soluble in water than carbon dioxide. Okay. All right. And so those are some examples of why we use the Lewis dot structure so we can figure out the polarity, because once we know the polarity of this, we can also take it one step further and figure out what type of polarity, what's going on there. And that gives us properties into what's called the intermolecular forces that tells us why things like a cup of honey is much thicker than a cup of water, okay? Because that's related to the intermolecular forces of the honey, which is related to the polarity of the honey, which is related to the polarity of the bonds overall, which is related to the atoms that are bonded to each other, okay? So it all ties in. It may not look like it does, but it does tie in. And all of this is related to those crazy electrons again. All right, so if you go through and if you did the other example, but if you look at ammonia, NH3, okay, here's a rule of thumb for you that will always give you information. That's ammonia, NH3. And if you go through the Lewis dot structure, you end up with a lone pair on nitrogen. Any molecule that has lone pair on the central atom, be it 1 or 2, the most you can have is 2, always is a polar species, okay, regardless of the polarity of the bond, because what's happening is that those lone pair take up space, and they're going to let me draw that angle here gets shrunk. And so that polarity of that bond, they're not going to cancel each other out, okay, because of the lone pair. So anytime you have a lone pair, like on water, water has 2 lone pair, extremely polar solvents. Ammonia's in group 5. You'll find examples where you, instead of nitrogen, you could be, I meant to say not ammonia, but nitrogen. Nitrogen in group 5, but right below nitrogen is phosphorus. So you could have an example of pH3, be the same structure, exactly the same structure, okay? Now, the one example that you can have all polar bonds, and you might be thinking, you saw how carbon dioxide has 2 polar bonds, and the direction of the polar bonds cancel each other out. Well, when you had the tetrahedral, the AB4, you might have all 4 polar bonds all going in that direction, away from the central atom. You can make those fluorines, all fluorines, or all chlorines or anything, all around, 4 chlorines or 4 bromines. Those are polar bonds between the carbon and the halogen. But in the configuration of tetrahedral, and when all of these are all the same element, other than hydrogen, okay, you cancel the polarity of those bonds, cancel each other out. Now, there's two scenarios where the polarity cancels out. One is an example of carbon dioxide. Okay, one's going in the other direction, the other's going in the opposite direction, and in the tetrahedron. And so if this was an example of carbon tetrafluoride, okay, if that was an example, which is tetrahedral, if you go through the scenario, okay, they all have polar bonds, 4 polar bonds. But being in the tetrahedral configuration, mathematically, when you go through it, all of those polar bonds cancel each other out. And so carbon tetrafluoride is a nonpolar species, even though it has polar bonds. Okay? The example that your book used is this, where you replaced one of those fluorides with a hydrogen. It still has tetrahedral, okay, but you have a carbon-hydrogen bond, which is nonpolar. And so the remaining 3 polar bonds do not cancel each other out. And so this example that's in your slide is a polar species. And if I replace another fluoride with a hydrogen, it remains polar. I can go all the way around the horn until I go back to all hydrogens, and then I go back to a nonpolar. So by playing with the atoms that have been bonded to the outside, I can go from nonpolar to polar, then back to nonpolar by changing what is bonded to the central carbon. Okay. Don't mistake in HCN that lone pair is nitrogen as the lone pair on the central atom, because the central atom for HCN is carbon. Okay. All right, so we did that example. Now, polyatomic ions. Well, let me direct you back to the periodic table. Okay, I use that quite a bit. On the periodic table, far left side, you see a table of the most common polyatomic ions that we work with. Okay, they're ions, though they are covalent bonded compounds. Okay, overall, because of the structure that they're in, they have a charge. Most of them are negative charge. You notice by the superscript negative. Okay, you only have one cation, which is the ammonium ion. A lot of these you use in your everyday life. You may not be aware of it. Hydroxide. If you ever used liquid plumber to unclog your drain, you use an hydroxide compound. Hydroxide is very strong against breaking of greases and fats, and most nonpolar material makes them very soluble. That also will destroy your tissue. So if you get some on your finger, it feels slimy. You might think that's the chemical. It's not the chemical. That's your tissue being denatured and broken down. So wash your hands immediately. A lot of the foods contain sulfates and nitrites. A lot of the wines, some wines contain what are called sulfites, which gives a lot of, I think they're vasoconstrictors, and they give you a headache if you're a wine drinker and you get a headache. Discarding drinking too much of it, but you know, for me, I can't even drink any wine because the sulfites give me one little drink gives me a terrible headache because of the sulfites. So these are polyatomic ions, and they come together as a unit. Okay, I discussed these a while back, and these are most of the ones we use most commonly. Next time you make chocolate chip cookies or you bake a cake or something, you may add some bicarb, sodium bicarb, baking soda. Okay, that's what that is. There's a formula right there. Function of that is to create carbon dioxide. When you heat it, that breaks down, makes carbon dioxide, which then makes your cookies rise. Otherwise, you're going to have flat cookies. Okay. So what we're going to do now is, you know what? It is 24. This is interesting. I'm stopping at the same slide as my 1 o'clock. Well, I'll tell you what, it's only got 5 minutes. Let me stop here because I need to do some background behind it, and I'd rather start fresh than start now and then redo it again on Tuesday. So Why don't we stop it here on slide 21? We did move forward. We are ahead. Okay. All right. So let me stop the share and end the